Transistors are the backbone of all modern electronics, and unlike resistors, capacitors, and inductors, transistors are active devices, which means they add to the circuit, considering you have an adequate voltage supply, of course. Unfortunately, transistors can be really hard to understand, considering you have to juggle two signals at once. That's why I've put together this video so that you can better understand how transistors work. There are several different types of transistors, but just for today we'll be focusing on BJTs. So, without further ado, let's dive in. Like I explained in the intro, we will focus on BJTs in this video. They are also known as bipolar junction transistors, and there are two types of BJTs, NPN and PNP. Both of them have 3 pins: collector, emitter, and base. You can always tell which one is the emitter since it has the arrow on it. Let's first begin by explaining why they are called either NPN or PNP. This comes from the way that they are manufactured. Using a process called doping, we can create silicon as one of 2 junctions, an N-type junction and a P-type. You will also notice that these 2 types of junctions are present in diodes, which have a PN junction. This is why you will often find diagrams of BJTs as diodes. But a BJT can do much more than act as 2 diodes, since 2 diodes placed back to back do not have the same effect as the continuous nature of the BJT's NPN or PNP. A BJT will amplify its base emitter current along the collector emitter path. Let me explain what that means step by step. First, we will define the base emitter current as the amount of current flowing through the base. You can easily identify this path by the arrow on the symbol. Just remember, the input current will always flow in this direction. In NPNs, the current will flow towards the emitter. In PNPs, current will flow from the emitter towards the base. This base emitter current will cause a much larger current to flow through the collector emitter path. You can also determine the direction of this flow by the arrow on the symbol. To better understand how this all works, let's draw a parallel to another real-life component. Some people will tell you that a BJT acts like a variable resistor, but that oversimplifies everything. Instead, I encourage you to think of a BJT as a current source. A current source is a component that will maintain a constant current across its pins so long as enough voltage is provided. It's similar to a voltage source, which maintains a constant voltage. A battery is a great example of a voltage source, since it maintains its voltage despite changes in the load. So, just remember that a transistor will do its absolute best to maintain a constant collector current flow, and it will drop a varying voltage across the collector emitter path just to keep that same current flowing. But just how much current will flow exactly? Well, you can determine that with the equation IC equals beta times the base current. Beta is the gain factor of the transistor, and you can find the value of this on the transistor datasheet. You will also likely find it underneath a different name, HFE. Taking the 2N3904 for example, we can find it under the on characteristics section. You will find a lot of different values here, which means that the value isn't exactly the most stable. But we will talk about ways you can deal with that later. For now, let's experimentally determine the exact beta value of this 2N3904. This is what our test circuit will look like. We will have the 2N3904, which is an NPN type BJT, a 100K base resistor, a 100 ohm collector resistor, and a 9 volt supply. Let's just run a quick calculation as to what the base current should be. Remember that the base emitter junction can be simplified to a diode. So what we have is our 100K resistor in series with this diode. Assuming a typical voltage drop of 0.6 volts across the diode, we should get a current of 84 microamps. If we take the middle gain value of about 100, then we can calculate an estimated output current of 8.4 milliamps. Now we should do an experiment to prove it. So here are the values that I collected. I measured a base current of 82.5 microamps and a collector current of 15 milliamps. If we solve for beta, we can see that this particular transistor has a gain of 175 at a collector current of 15 milliamps. This value is within the datasheet's range, so the math checks out. And for further proof that this transistor acts like a current source, I'll remove the resistor and connect the pins directly to the supply rails. and we will still measure that same 15 milliamps of current, despite changing the load. Let's run the experiment again for a PNP. In this case, we'll use the 2N3906. Take note of the direction of the arrow on the transistor. We will have to make current flow in that direction. So this time, we will connect the resistors to ground. The base current calculation is still the same, but the conceptual circuit has the diode at the top instead. Anyways, here are the results for the PNP version of this test. We got a base current of 82.5 microamps and a collector current of 20 milliamps. That means we have a gain of 242. The same still holds true in that the current holds even when changing the load. However, if we go in the opposite direction and increase the collector resistor up to 100K, then we will find that our once stable current drops down to a measly 88 microamps. To explain this phenomenon, let's take a look at the operating modes of BJTs. BJTs have three useful regions of operation: the active or linear region, saturation, and cutoff. Cutoff is easy to explain, since it simply means that the transistor is just off. The active region is what the previous experiment just displayed. The transistor will drop whatever voltage is necessary in order to keep the constant current. Saturation can be shown at the end of that experiment though, with the 100K collector resistor. The base current was trying to keep the current constant through the transistor, but the resistor simply was way too much for the power supply to get over to maintain that current. In other words, saturation occurs whenever the transistor is trying to deliver that constant current, but the impedance is just too high for it to reach. In other words, saturation means that the transistor is fully on. We can detect when we have reached saturation by measuring the collector emitter voltage. If the voltage drop is less than approximately 0.6 volts, then we've reached saturation. The 0.6 volts comes from the base collector junction, which is also a diode like I explained in the beginning of the video. So, in saturation, the transistor becomes closer and closer to a short circuit. To demonstrate, I'll use this setup. We will have our function generator connected to the base through a 10K resistor. The collector will have a 1K resistor to the positive rail. The oscilloscope will measure the current through the transistor by using a current sampling amplifier. It will also measure the voltage on the base resistor. We will apply a 40 Hz triangle wave to the base resistor so that we can experimentally get different base current values. We can calculate that with a 1K resistor and a 9V power source, the max current that we could get is 9 milliamps, no matter what the transistor does. As you can see, the ramp wave goes through and applies different currents. At first, in the linear region, the transistor is in the active region and it follows the current. However, we reach saturation at the end and the current flatlines and it can no longer go any higher. Both saturation and active operation have their places in design. Saturation is useful when you want your transistor to act as a switch, since you aren't interested in the relation between the base current and the collector current. You only really care whether it is fully on or fully off. In saturation, you not only satisfy this on or off requirement, but you also waste much less power through the transistor, since it has a very low VCE voltage drop. Active operation is more useful for amplifiers in quickly switching signals, as you'll see later in this video. There are three basic types of BJT configurations: common emitter, common base, and common collector. Let's start with common collector. The common collector configuration typically has the collector connected to the positive rail for NPNs and the negative rail for PNPs. The emitter has a resistor and the base has the input signal. Here, the output is not determined so much by the base current, but rather by the diode drop from the signal on the base. This essentially creates a situation where the output is 0.6 volts lower than the input. This makes for a good signal buffer since we copy the input signal, but the BJT drives the load. This means that we can keep our weak input signal from having to drive a large output load. Next up is the common emitter. This is a similar setup to the one we had during the experiment. Here, the emitter is tied to the negative rail for NPNs and the positive rail for PNPs. In this case, we can build an actual amplifier because we can take advantage of the current gain inherent to the transistor. This is, of course, if we remain in the active region. If we instead go into saturation, then we reduce down to a simple inverting switch that is either on or off. More on both of these ideas in a bit. And finally, we have the common base configuration. This isn't a very common way to use a BJT, but it's still important to know about. In this case, the input signal is applied to the emitter, and then we get an output on the collector. A lot of the time, these common base designs are paired in series with a common emitter configuration to form a cascode. These cascodes have the advantages of both types, namely a high input impedance and a large bandwidth. But more on cascodes and the common base configuration in another video. Let's begin with the BJT as a switch, since that is the simplest configuration of all. Let's say that you want to switch a high voltage load, like 3 LEDs in series, which would have a voltage drop of about 9 volts. But the source which it comes from is a low voltage, such as a 5 volt microcontroller. How can you toggle the load without damaging the 5 volt circuitry? Well, what you can do is simply apply a small base current to the transistor, and then we'll get the full load flowing from another 12 volt power source. In this case, we go into saturation, which is advantageous since we have a smaller power loss across the transistor. And while switching loads is useful, we can do a lot more than just that. You may have heard of logic gates before, such as AND, OR, NOR, and so on. Well, we can create those by using these transistors. Here's the simplest BJT Logic Gate, which is an inverter. When we apply a high signal to the input, the NPN goes into saturation and turns on, so it has a very low voltage drop. This essentially causes the output to be pulled down to ground, giving us a 0 on the output. However, when we put a low signal into the NPN, this creates a cutoff situation, and the transistor is off. This means that the collector resistor pulls the output up to the supply rail, giving us a 1. This inverter is of the RTL logic type, and you can expand it further by chaining transistors together to make OR gates, AND gates, and everything else. And while the digital side of transistors is interesting, you can do a lot more with them from an analog perspective. Here's the common emitter circuit that I showed you earlier. This circuit is also known as a Class A amplifier. So let me explain how it works. Remember that ramp wave experiment that we conducted earlier in the video? Well, before the transistor reached saturation, we were actively amplifying the input signal in the active region. This is because of that current gain. A higher input voltage will cause a higher base current, which in turn causes a higher collector current. A higher collector current will drop more voltage through the collector resistor, and we will end up with a proportional signal in the output. Let's imagine that we have a very weak and small audio signal, like this sine wave, and we want to drive a speaker so that we can listen to it. Well, we can't connect it directly, so we will have to amplify it. The first thing that we'll do is AC couple the signal to our transistor amplifier by using a capacitor. We do this because we don't want to amplify any DC from the input signal. We just want to keep the AC audio part of it. But when we look at our output signal, we will see that not much of the signal is actually getting through. We only see these tiny dips at the top of the waveform. So let's take a look at the base voltage. Here we can see that the voltage is beneath our ground point, and its maximum is 0.74 volts. This shift downwards below 0 is caused by the connection through the diode, which limits the DC point of our sine wave. To fix this, we need to do what's called biasing. Ideally, we want to bias the transistor such that the middle of the waveform is in the middle of the voltage supply. So, for our 9 volt power supply, we'd like to set the bias point to 4.5 volts, which is half of 9 volts. With our 9 volt supply, we'd need 2 milliamps flowing to the 2K2 collector resistor to reach our bias point when no signal is applied. We could try to do it like before, with a single base resistor to VCC and determine the current by using beta. This kind of works, but it isn't exactly the best in circuit design. You should know by now that the current gain isn't exactly the most stable figure, and it varies from transistor to transistor, different temperatures, and different currents. Rather, what we want to do is to set up the circuit such that it isn't dependent on beta. We can start with what is called emitter degeneration. This is when we place a resistor on the emitter of our circuit. Now we can get a predictable current flowing through the collector, and here's how that works. Remember from the previous section where I showed you an example of a common collector setup and how the voltage at the emitter is 0.6 volts lower than the input? The same could be said here. So, this means that the input signal controls the emitter voltage. This same emitter voltage determines the current for the emitter resistor, because we have a particular voltage drop across this resistor. We can find this current drop by using Ohm's law. And since the collector must flow through this same path, this is also the same current that flows through our collector. That same collector current generates an output voltage through the top resistor. So, if we make the emitter resistor 470 ohms, then we would need the emitter to have a voltage of 0.94 volts. If we keep in mind the voltage drop of the diode, then we can calculate that we need a voltage of 1.54 volts on the base. We can create this voltage on the base with a voltage divider. I selected resistor values of 22K and 4.7K, which give us a calculated voltage of 1.58 volts. This is close enough to what we calculated, and with this setup we can get our real measured bias voltage of 5 volts on the output. This setup actually reveals a new equation that we can use. The voltage gain of our amplifier is equal to the negative collector resistance divided by the emitter resistance. So you'll notice that the beta is not involved at all. Alright, this should be sufficient. So let's apply our signal again. And wow, the amplification worked. The input signal was 1 volt peak to peak, but now our output signal is 3.9 volts peak to peak, centered around 5 volts. This gives us a voltage gain of 3.9 times. Let's switch out the transistor for another and see if it remains stable. And look at that, we have the same results across different transistors. The amplification is no longer nearly as dependent on beta as it once was. Let's try to connect our amplifier to the speaker now. Don't forget to add another AC coupling capacitor on the output, since we don't want to waste DC power on the speaker. The setup works, but it's inaudible, I can't hear anything. The load from the speaker is just too much for our current setup. In an attempt to fix this, I simply reduced all the resistors by a factor of 10. And we can hear it now, but it's still barely audible. Unfortunately, Class A amplifiers are not at all efficient, so increasing power output further would be difficult. At the very least, you can still use it as a very simple voltage amplifier. Before we go any further, we really should expand our understanding of the BJT. Let's take a look back at our common emitter amplifier again. If we use our equation of gain, negative collector resistance divided by emitter resistance, with the most basic form of the circuit, the one without an emitter resistor, then we'd calculate that the transistor would give us infinite gain, since there's zero resistance. Now, this is obviously not possible, and well, you can thank transconductance for that. The idea behind transconductance is that the current through the collector is not determined by base current, but rather base voltage. The equation behind this idea is the Ebers-Moll model, which comes with the equation IC equals IS times e to the VB over VT minus 1, where IS is the reverse leakage current and VT is the thermal voltage for the transistor. You can use another equation, KT divided by Q, to find VT, where K is Boltzmann's constant, T is the temperature in Kelvin, and Q is the charge of a single electron. At room temperature, the thermal voltage is 25.67 millivolts. And this is the result that we will use for the rest of the video. Now, I understand that all these equations all of a sudden can be really confusing. So let's get to the point. Using the Ebers-Moll model, we can derive the value of transconductance. Gm equals the collector current divided by the thermal voltage. Now, since transconductance is the value with the unit of Siemens, we can easily convert this into a more useful form. If we invert conductance, Siemens, we get resistance, or ohms. This inverted value is the emitter resistance of all BJTs. You can solve for it by using Re equals the thermal voltage divided by the collector current. Here is how you can imagine the placement of Re. It's simply like a resistor placed in series with the emitter, so both the base and the collector paths have to go through it. Using this, you can see why a grounded emitter follower doesn't have infinite gain, since there is actually a very small resistance on the emitter. This also shows you why emitter degeneration is so important. Without it, small changes in our collector current would massively change Re, and therefore our gain, causing distortion and instability. Even a small change in the collector current from 1 milliamp to 2 milliamps will double the gain of our amplifier. To fix this, an emitter resistor of our own is not current dependent, and it will keep our gain and current stable through the transistor. So, the main takeaways from this section should be that first, you can determine the collector current by using the base voltage if you wish, and second, there is always a small emitter resistance which is unstable. So, from this point forward, you can determine whether your analysis needs these two properties in order for you to properly examine the transistor circuit. Like I explained much earlier in the video, transistors are like adjustable current sources. The problem is that, by themselves, the adjustable part is hard to predict and it varies with several factors, making it rather unpredictable and unstable. However, with a few extra components, we can remove most of the uncertainty and make a much more stable current source. Let me introduce the basic current mirror. It consists of just two transistors with their bases and emitters tied together. One of the transistors will have its base and collector tied together. The base collector junction being tied together essentially reduces this BJT down to a single diode. Now, the current flowing through this diode will inevitably cause a voltage drop. Since both transistors share bases, they also share the same base voltage. This creates the end effect that the current through path 1 is roughly mirrored to path 2. Now, to turn this into a current source, we can simply set the current in path 1 with a single resistor. You can solve for the current by considering the simplified circuit here. Just a resistor and a diode. With VCC being 9 volts and a 10K resistor, we should get a current of about 840 microamps. If we measure the current on the mirrored path with a load of 100 ohms, we also get 840 microamps. Even if we change the load to 1 kilo ohm, we still get 830 microamps. So it's relatively stable. And the circuit will work so long as you don't force the mirror transistor into saturation. Either way, this is a big improvement over the single transistor current source. A potential alternative to the current mirror is what is commonly referred to as a current limiter. It also uses 2 transistors, but 3 resistors. The first transistor, Q1, is there to pass current through our load. R1 simply allows Q1 to turn on and let the load pass through. However, we have negative feedback in the sense resistor. This resistor will drop voltage proportionally to the amount of current flowing through the load according to Ohm's law. This resistor forms our negative feedback portion of the circuit. When the current is high enough to drop at least 0.6 volts through the diode of the base, then Q2 starts conducting. This in turn starves current from Q1, which will cause it to conduct less, which results in less current for the load, which causes less current to be flowing through the sensing resistor, which reduces its output voltage, which turns off Q2, and eventually we reach an equilibrium point in which the current is maintained across the load resistor. Now we just have to decide on the values of the parts. R1 and R2 should both be somewhat large in order to reduce power losses. So I chose R1 to be 10K and R2 to be 1K. Now, R sense is where we get to choose the current limit. Now remember, the current is determined by Ohm's law, and V is stuck at 0.6 volts because of the diode. Let's say that we want to drive an LED at 10 milliamps. So we can use Ohm's law to solve for resistance. Using these values, we can calculate a resistor value of 60 ohms. Now, I don't have a 60 ohm resistor, so I chose a close value of 56 ohms. Now, if we place our LED and measure the current, we get a value of 11 milliamps. This is really good, and we can even change the supply voltage and still get that same current flowing through the LED. You may eventually come to a point where you need more gain from your transistor. In that case, you should take a look at the Darlington transistor. It's simply made up of 2 single transistors of the same type together in order to form one larger virtual transistor. What happens here is that we essentially have a BJT that drives the next BJT. In fact, we get a new overall current gain for this pair. The current gain of the Darlington pair is simply the product of the 2 that make it up. So, if we use 2 2N 3.4s and assume gains of 100 each, then we'd get a current gain of 10,000 from the initial signal. This means that we don't have to load down the input stage so much when driving the transistor, since we would need far less input current than a single transistor on its own. It's also worth mentioning in the same section another transistor pair, which is called the Z-Cli pair. It has the same end result as the Darlington, in that the current gains of each transistor are multiplied together. The big difference here is that the two transistors are of opposite types. One is an NPN and the other is a PNP. The overall pair acts like the first transistor in the series. For example, I used a Z-Cli pair in my linear power supply video. Instead of passing current through the LM317, I instead routed it through a Z-Cli pair. It is a PNP type pair because the first transistor is a PNP. Meanwhile, the 2N3055 NPN power transistor did the rest of the heavy lifting. Well, this video should provide a good starting point and reference for BJT circuits. Don't worry if you don't completely understand it. It's a confusing subject. I'd also like to point out that my work with transistors isn't done yet. We still have to cover MOSFETs, so stay tuned for that video. Anyways, if you've enjoyed this video so far and learned something new, please consider subscribing so that you can see my future videos. Also, check out my Buy Me a Coffee page. With your support, I can keep getting components that I can use to experiment with and make new videos. I'd also like to give a big thanks to Mr. Dev Null and Cognizant for being longtime channel supporters. You both have really made all these videos possible, so thank you. Anyways, thanks for watching. Have a good one.